Chris, please.
Oh, I gave you the title of my talk an hour or so ago.
Oh, okay. So I didn't check my email in the last 40 minutes or so. So okay.
Yeah. Okay. But anyway, I got a message from someone this afternoon, which meant maybe like 4:30 India time. And I was kind of shocked that someone was emailing me at that hour. So I decided that I should finally give a title and abstract. But my title, I think, was, as it often is Geodesics in first passage percolation. And what I want to do is I want to talk about a few results and also a few conjectures, and then kind of outline some possible ways one might go about trying to prove these conjectures. So for sake of specificness in this talk, I'm going to always do first passage percolation on the nearest neighbor graph on Z2, and my distribution will be, so I will always have a exponential 1 distribution on edge weights. And these will be IID. Nothing particularly special about this, but this is a nice distribution. If you're going to pick a distribution to prove something about, then it might as well be this one. And so what is the, so what are kind of the fundamental results in first passage percolation? So we have B of t are the set of all Z in Z2 such that the passage time from the origin to Z is less than or equal to t. So this is the set of all points that we can reach from the origin in time t. Now, so then the theorem, so one of the earliest theorems in first passage percolation, which is due to Cox and Durrett, is that properly scaled, so I take B of t and I scale it by 1 over t. B of t so 1 over t, B of t converges to some shape B contained in R2, where B is constant. And this convergence happens almost surely. So I have to pattern things up, but the set of points that I can reach in time t is growing linearly, like some shape in the plane, times t. And what do I know? I know that B is constant. It is symmetric, so it has all the symmetries of Z2, and it is convex, non-empty, and it is not everything. And beyond this, nothing is known. As the last time I checked up to scaling, once you scaled this set, then you didn't know anything more about the shape. Does it look like the L2 ball? Does it look like the L infinity ball? Nothing has been ruled out. So it could be any possible shape that satisfies these conditions here. So now there have been a number of theorems in first passage percolation that are of the form, if we know something about this set B, then we know something about, we can say something about the set of geodesics in first passage percolation. And my main theme of this talk is going to be, we'd be better off if we thought about it the other way around, and we thought about, if we can say something about the set of geodesics, then we might be able to say something about what this set B is. So this set B is very mysterious. The Cox Durrett theorem is from the mid-70s, I believe. And we still don't know anything. We have really learned essentially nothing about this, not just for this one particular distribution, but for almost every distribution, we have learned very, very little about this set B in the last half of a century. And therefore, I will argue that although we have these really beautiful theorems that say knowledge about what this set B is gives me knowledge about the geodesics, then I'm going to say we might be better off if we tried the alternate approach of learning things about the geodesics and then using that to say something about B. So what I want to do is I want to kind of say first some of the main things that are known about, that are theorems that say, if we know facts about B, then what do we know about the geodesics? And then I will kind of say things that I would like to prove about the geodesics and how we might leverage that to saying something about what the shape is. So one thing I've learned in the pandemic is that I would not be a good disc jockey, because I do not like the feeling of just kind of talking and broadcasting out into the ether and having no idea who is out there. So I will stop now and see if we can get a question.
Any questions? There doesn't seem to be any questions so far. I don't know if you can see us, Chris, but yeah.
No, I can't. I probably, yeah, I don't know.
There should be a view of the lecture hall in one of the logged in Zoom accounts, but I don't know actually how you can see it.
Okay, it's at least better. Yeah, so I guess I can pin this here. Then I can at least see. I can at least see people. Okay, so the best theorem that we have is, so this is due to Newmann and Pisa. And what does it say? It says that if the boundary of B is uniformly curved, then the fluctuation of geodesics is at most into the 3/4 plus the low of 1. So if I take any 2 points, 0, 0, and B, and the distance between them is n, then I can draw some window here, some cylinder, where this size here is into the 3/4 plus the low of 1. And if I look at the geodesic here, it will stay in the cylinder. So that's what I mean by the fluctuations are at most into the 3/4 plus the low of 1. So this is the geodesic, 0, 0, comma B. And with high probability, it stays inside of this cylinder. And by uniformly curved, well, the boundary is this nice curve in the plane. So I can calculate the curvature of it, and this is stronger than needed. But we could say the curvature is always between 1 and 100. It's always bounded below by something, and it's always bounded above by something. So if the curvature always exists, and there's a uniform bound below and uniform bound above, then we get this result here. That as n goes to infinity, the chance of this geodesic staying in the cylinder is going to 1. And so this is a really beautiful result where in spherically symmetric models, we are actually able to say something about the fluctuations of the geodesic. But in first passage percolation, it doesn't help us to say anything about the geodesics. Okay, and the second result is due to Damron and Hanson. And it says, so one way of saying it is if B is strictly convex, the boundary of B is differentiable, then in every direction there exists a unique geodesic almost surely. So if I choose some vector here, and I choose a point, then I can find a geodesic here, which, when I scale it, is asymptotically going in this direction. There's going to be one such geodesic, and it's going to be coalescing. At every point in the plane, it will eventually join up with this. And with probability 1, there will be this geodesic, and there won't be any other geodesics which have this asymptotic direction. So, but we do not, we don't know this for any distribution. In particular, we don't know it for the exponential distribution. So we have these two theorems that say, if I know something about the shape, the limit shape, then I know something about what the geodesics look like. And these are really beautiful theorems, but we've never really been able to use these theorems to say anything concrete about geodesics in first passage percolation, because we do not know anything about the limit shape. So, but again, so are there any questions about either of these theorems here?
There doesn't seem to be any questions still.
Okay, so I'm going to give you an alternative approach which can prove as many theorems as we can prove using these two beautiful results, well, which unfortunately is 0, but if we why? So I want to say that we might have a better chance to try and say something about, to study geodesics as much as possible, and then hopefully this will give us some knowledge about the shape. It's it's not a particularly concrete plan, but it does have some possibility of success. So I'm going to say some kind of conjectures about geodesics, some theorems about geodesics, and how we might be able to bootstrap from those conjecture about geodesics to give us some knowledge about the limiting shape in first passage percolation. So there's a theorem. There's a general belief or conjecture due to Newmann. So which is, so it's basically that result that the conclusion of the result I just had from Damron and Hanson that says in every fixed direction, there is unique geodesic, almost surely. And if this is true, then in random directions, there exist two geodesics. Because if I'm going to get a geodesic in every direction, then there have to be these spots where I split. And then if I take the direction of this geodesic here and the counterclockwise limit of all the geodesics that are clockwise of that geodesic, that will, or I guess the counterclockwise limit of all the geodesics that start here, go through here, and then continue on this edge, that will give me a different geodesic, and it must have the same direction as this geodesic here. So there have to be these random directions where I get multiple geodesics, and I expect to see only two geodesics. So I saw the microphone was floating around. Did someone have a question?
Thank you. I think you answered it, Chris. I was wondering if you thought there was just exactly two or at most two.
Yeah, it should be exactly two. And yeah, and in various settings, people have been able to prove that in all directions simultaneously, there are only two geodesics. But in standard first passage percolation, it's still unknown whether there are any directions with more than two geodesics. Okay, so but what we do know is, so we know that there's at most a countable set of geodesics where the probability of getting multiple geodesics is positive. So what do we know about geodesics? So for every geodesic, so I take a point here and I get a geodesic, x1, x2, x3, so on. So there exists a Busemann function. Which call that fg of yz, which is the limit as n goes to infinity of the passage time from y to xn minus the passage time from z to xn. And this exists, so this exists fairly easily. And then what do I know? So for every geodesic, there exists this Boussimon function, and it is approximately linear. So this is asymptotically linear. So there exists some linear function such that f g of 0 z minus rho of z. So there exists some rho, some linear function rho, such that the difference between these things here is equal to little o of z. And so this is a result of Daniel Alberg and myself, is that for every realization of first passage percolation, almost every geodesic has an asymptotically linear Boussimon function. And it turns out that I think that looking at this linear function here is a better way to characterize geodesics than direction.
Chris?
Yeah.
So are these Boussimon functions, are they stationary or not?
So you can, so yes, so they are stationary. Although I said something, so for every, so what is the right thing to say? There is some fixed set of rho, some fixed set of linear functions, such that there almost surely there is a geodesic whose Boussimon function is growing linearly with that, and these are stationary. But the thing that I said was a little bit stronger, which is that for every geodesic, the Boussimon function is asymptotically linear. And we don't know, though, for every geodesic, there's going to be some stationary distribution. What happens in kind of the distribution, in the directions where I get multiple geodesics, I'm not really sure I can say that one or the other of those gives me a stationary distribution.
I have a follow-up to that. You
Yeah.
also mentioned that almost all geodesics have linear Boussimon functions. In what sense do you mean almost all?
No, all geodesics.
All geodesics, okay.
So for almost every omega, almost every set of edge weights, all geodesics have all geodesics have the Boussimon function, and this is asymptotically linear. With probability 1, it's asymptotically linear for every geodesic, starting at any point in the plane. So the set of rho geodesics, whose Bussmann function grows like rho is an almost sure constant. So the first conjecture that I have is okay, this is my least favorite part of online lectures, is that when whiteboard does something that I cannot understand, and it refuses to make my screen get any bigger. Okay, so then I just do some random thing, then eventually it gives me new white space. But so my conjecture is that this set of linear functionals linear functionals on the plane has one element. Well, this set of linear functions is indexed by the 0 line. Any linear function in the plane. I need to know two things. I want to say that it has one direction that it's 0, and then I need to know how fast it's growing in some other direction. And I want to say that for every line through the origin, there exists a geodesic whose Bussmann function has a level set that is asymptotically parallel to that line. So this set of linear functionals has one whose level set goes in any direction. So for any direction, there exists, with probability 1, there exists a geodesic whose Bussmann function has the level set parallel to that line. So this is a concrete question about geodesics, which I think is fairly tractable, is reasonably tractable, although I worked on it for a while without a whole lot of success. But I think it should be possible to answer this question. And then I want to bootstrap from proving this conjecture to say that, and then I want to say that for any direction. So this is the second conjecture. For any direction, the probability that there exists for any direction z, the probability that there exists two geodesics with direction z is equal to 0.
Chris, there is a question in chat from Ken.
Oh. So Ken asks about the limits of this conjecture. I mean, so so stationary ergodic, I would not want to say this for stationary ergodic, because so this gives me a chance to say one of the most beautiful theorems in first passage percolation. So if I consider not independent edge weights, but just stationary and ergodic edge weights, then I can make the limit shape be whatever I want, provided what I want is for it to be symmetric and convex. I can get it to be any symmetric convex shape that I want, using symmetric stationary and ergodic things. So no, I definitely do not want to consider I do not want to consider stationary and ergodic. I want to consider independent and the edge weights at for each edge are a continuous random variable. Because if I have these two conjectures here, so these two conjectures imply that there is that the limit shape is differentiable. So these two conjectures imply that the limit shape is differentiable. And why is that? Well, how could a convex set in the plane not have a boundary which is differentiable? It's got to have a sharp corner. So here, I could, so if this is my set B here, and if I've got a sharp corner here, then I get two lines which are tangent to B at this point. They're two different lines. And in each, parallel to each line, I get a geodesic. And the geodesic has to be pointed in the direction of that point where there's a sharp corner. And so then if I had a sharp corner on the boundary, so if the boundary of the shape were not differentiable, then I would have multiple geodesics. If conjecture 1 is true, then I would have multiple geodesics in that direction, and that contradicts conjecture 2. So I definitely don't want this to be true in the stationary and ergodic case, because what I because I know that I can get limit shapes which do have sharp corners. And in the one example that I know well, these conjectures don't hold. So this is the first way that I hope to bootstrap from knowledge about geodesics to knowledge about the limit shape. So are there any questions on this? Okay. Then the next thing that I want to talk about is how I might be able to say that the limit shape is strictly convex. And how do I hope to do this? So now I want to take a geodesic here. And I want to look at, so I've got some point here, x0, x1, x2, and so on. Oh. Okay. Okay, I think I got my screen back. So I have a geodesic here. X0, X1, X2, and so on. And I would like to say, I'd like to look at the environment along this geodesic. And how will I do this? Well, I'll take a box, say, first I'll take a 3x3 box, and I'll look at the environment around x0, the environment around x1, and so on. And I would like to, and then I'll take a limit by just looking at, so I'll say ek of z is the k by k environment around z. And then I want to look at 1 over n, the summation of point mass at EK xi. Summation I goes from 1 to n. So this is a measure on edge weights on K by K grid. And my hope, and then I don't know if this converges. I would be really happy if it converged. But I don't know that it converges. And then I would like to not just look at K by K grids, but once I know, see whether this converged, then look at larger and larger K. And this will give me a measure witnessed along the geodesic. And then I could ask, well, I don't know that this converges, but I can construct subsequential limits. And then the question is, can I construct multiple subsequential limits? And so the conjecture is no, I can't. That there's a unique subsequential limit. So that this in fact, it does converge. So the conjecture is either, yes, this converges, or no, I can't construct multiple subsequential limits. And so then, if I could do this, then there are certain, I could rule out certain possible boundary shapes. So the one case where we know something concrete about what the limit shape is a result due to Damron and Oppinger, where they looked at certain models where the oriented percolation, so the smallest edge weight you could have was 1, and 1 occurred higher than the oriented percolation threshold. So I get this cone, this oriented percolation cone. So the lowest edge weight is 1, and 1 occurs more often than the critical value for oriented percolation. So I get this cone that I have for oriented percolation, and then they show that if I make certain other, then I can show that. So I get a flat piece along this here. So there's a flat piece here. This is due to Cox and Durrett. They showed that you get this flat piece here. And then what Damron and Oppinger said was at the boundaries here, you still get something that's differentiable. at those points there and there, at the boundary points of the cone. So for this, now, what would this tell me? Well, I say that this contradicts the conjecture that I had for these environments along the geodesic converging. And why is that? So again, going back to Ken's question, this is kind of assuming that I have some independent and continuous distribution for my edge weights. So for each geodesic, since it's differentiable here, I'm going to get a collection of geodesics that are getting closer, whose directions are getting closer and closer to this direction. And I'm going to get a collection of geodesics that are clockwise, getting closer and closer to this direction here. So the two boundaries of the cones. And and for each of these, I can get some limit on the, I can get some measure along the geodesics, and these should be converging as the geodesics converge. So I should get one limit that corresponds with this edge of the cone here, and another limit that corresponds with this edge of the cone here. And those should both correspond to the one geodesic which goes in the direction of the flat piece. So then I would like to use this to say, if there are no multiple geodesics, then we don't have anything like this. And in fact, the limit shape B is strictly convex. So I want to prove some statement about geodesics, in particular that the empirical limit along one of these geodesics converges, and then use that to say that the limit shape is strictly convex. So these are two conjectures, or I guess three conjectures about geodesics and first passage percolation. One had to do with, I get in every direction, I get a Bussmann function whose level set is parallel to that direction. And then also there are, in no direction are there multiple geodesics, and use that to say that the boundary shape is, the boundary of the limit shape is differentiable. And then I want to use this third conjecture about the limit of the environment along geodesics to say that the limit shape is strictly convex. And I hope that these statements about geodesics, which have proved at least somewhat tractable, might give us insight into the limit shape in first passage percolation, which has so far almost totally eluded us. Okay, so I'm out of time, so that means that I should quit here. So are there any more questions?
Well, questions? Yeah, go ahead.
So Chris,
Yeah.
at each end, at either end of the flat spot, you could have essentially the same empirical measure, but why should that say that the flat spot doesn't exist?
So you can it's pretty easy to say that when I take a limit of geodesics that is approaching one side of the cone and a limit of geodesics is approaching the other side of the cone, I'm going to get different measures. Because by looking at this environment, I can see which way the geodesic is moving. And in one direction, it's going to be moving parallel to or asymptotically in the direction of one edge of the cone, and for the other one, the geodesic is going to be moving asymptotically in the other direction of the cone. So it's not too hard to say that these limits have to be different. And therefore so if I can show that these exist, then I will have that then I'll have that I cannot have, then this one geodesic has to have either one thing as its limit of along the geodesic, limit of the environments along the geodesic, or the other one.
Other questions? Was there anything in the chat?
Yes. I have a question.
Yeah.
Just following up on the last question, it seems like if the geodesic is, if you have the facet there, that the geodesic can go back and forth among the directions of the facet, that cone of directions, without any cost, and it can do that even on very short length scales. So it could be that when you look at your K by K box, that you're gonna see, like, elbows in the geodesic all the time, typically, that it's just changing all the time what direction it wants to go within that cone of directions. So would you necessarily get two different subsequential limits if the times when it's clearly going in the, let's say each extreme direction, or you pick two different directions and say, pick the times when it seems to be going in that direction, would there really be such times? Could that be guaranteed?
Yeah, so I mean, if it is, so what we know in the oriented percolation case is you can go arbitrarily close to one edge of the cone, and then you can shift up and go close to the other edge of the cone, and you can do this. And so that gives you, I mean, in essence, that gives you two different limiting measures that you see along geodesics. Because sometimes your geodesic is going in one direction and sometimes it's going in another direction, and it can do this for longer and longer periods of time. So that will give you two different measures. And that's because if I know the measure around if I know the environment in a box, then I can figure out what the geodesic has to be. So if I know the environment in a large enough box, then I can deduce from that what the geodesic has to be. And if the geodesic really is going back and forth, then this is going to give me multiple subsequential limits.
Okay.
So I can argue kind of hand waving that if it's not strictly convex, then my geodesic should wander back and forth close to one edge and close to the other edge, and that should give me multiple subsequential limits. And there are certain circumstances where I can make this hand wavy argument. I can make the hand wavy argument rigorous, But it's not a terribly, I mean, but it would be nice to just kind of have a general statement, well, that says if you had this flat piece, then the geodesic must go back and forth between the two edges of the cone.
All right, Chris. Yeah, thanks. Thanks for that.
Okay. Yeah, I'm sorry I wasn't able to make it. But I hope the conference has been going well.
Yeah, it's at the end, so yours is the final talk. So we're at the end, but yeah, it's okay. So Arjun, you want to